Good day. So we're going to talk about the types of functions. So for the types of functions, we're going to discuss some types of it, but be informed that functions are not limited to these types alone, okay? So first, we have the polynomial function, the linear function, the quadratic function, the constant function, the rational, radical, exponential, logarithmic, and piecewise defined function. So first, for the polynomial function, it is defined by the equation f of x is equal to a sub n x raised to n until a sub 0, such that n here is a non-negative integer, meaning it should not it shouldn't be, like, for example, -1 or any negative, and it should be an integer and not a decimal or a fraction. And a sub 0, a sub 1 until a sub n are real numbers. It could be any number. It could be square root of 5 or 1/4 or 1 or -1. Okay? So let me give you an example for polynomial function. So for example, f of x is equal to x squared minus 3x plus 2. Okay? So it has elements x squared, x, which are variables, and 1, -3, and 2, which are the a sub n's. Okay? Another example is g of x is equal to square root of 5 x cubed minus 2x plus 3. So this is another example of a polynomial function because it has elements, the a sub n's and the variables. Okay? Another example is this. h of x is equal to 1. Why? Because although we don't see any variable here, a sub 0 is, wait, I'm sorry. Okay, this one. Okay, although we don't see any variable here, a sub 0 is still a part of the equation. So recall that f of x is equal to a sub n, x raised to n, plus a sub n minus 1, x raised to n minus 1, until, until a sub 0. And a sub 0 here is a constant. Okay? And we can regard the other terms as 0. Clear? Okay. So let's proceed with a linear function. So a linear function is a type of a polynomial function, and it is defined by this equation. F of x is equal to mx plus b, such that m is called the slope and b is called the y-intercept. So for this, we have a graph which is called a line. So example for this, f of x is equal to 2x minus 1. So make sure that the equation for this, or the function, is or has a degree 1. Okay? Degree means it's the highest exponent. Oops. This one. Okay. It's the highest exponent. So the highest exponent here is 1. There's 1 here. Another example is g of x is equal to x. So again, this is an example of a linear function. So the slope here is 1, and the y-intercept here is, or the b here is 0. Okay. Another example is 3x plus 7. Okay, so this is again a linear function such that the slope is 3 and the y-intercept is 7. Okay. Now, with regard to the graph, if the slope is positive, the graph looks like this. Okay, so it goes upward from the lower left until up to the upper right. I'm sorry, lower left going to upper right. Okay, and then if the slope is negative, then if the slope is negative, our graph would be from upper right or upper left, sorry, going to lower right. Again, so the linear function has a graph which is a line. Next, quadratic function. So quadratic function is defined by the equation f of x is equal to ax squared plus bx plus c, whose graph is a parabola. So as we can see here, the highest exponent for the quadratic function is 2. Okay? So we have here, if the function has the degree 2, then automatically it is called a quadratic function. Okay? So the graph for this is a parabola. Let me give you an example. Example is f of x is equal to x squared minus 2x plus 1. Okay? It has a degree 2. Okay? The 2 here. Another example is x minus 3 squared. Why? Because if we expand this, it's x squared minus 6x plus 9, which is a quadratic function because it has a degree 2. Another example, h of x is equal to x minus x squared. Again, although the x squared has a negative coefficient, we are concerned with the degree of the function, and the degree of this function is 2, meaning this is considered as a quadratic function. Now, the graph for quadratic function is a parabola. Okay, so parabola looks like this. Okay, if the coefficient of x squared, let's coin this as a. If a is positive, then our graph would look like this. It goes upward. But if the coefficient of x squared, which is a, is negative, then the graph looks like this. It goes downward. Okay. Next, constant function. So constant function is still a polynomial function, but it is a special type of polynomial function. And this is defined by the equation f of x is equal to c, such that c is any number from the real numbers. Okay? And it has a graph which is a horizontal line. So, let's give an example for this. So for example, f of x is equal to 1. Okay? The number here could be any number. So another example is g of x is equal to square root of 5. Square root of 5 is still a constant. It doesn't have any variable with it. Okay? It doesn't have any term with a variable. Another example is g of x is equal to, let's say, logarithm of 5 to the base 3 plus 2. Because these are all numbers and it doesn't have any variable. Okay, so this is still a constant. Now, according to the definition, the graph is a horizontal line. So let's say we have f of x is equal to 1. So the graph for that is, we have the Cartesian plane, and we have 1 here. So the graph would be horizontal line. Okay? So what does this mean? Meaning, for every x, for example, this 1. So we have here negative 1, 1, 2, 3, negative 2, negative 3. So for every x, the value of y, or f of x, is always 1. Okay? So it doesn't change. It's just constant. Okay? So, next, rational function. So rational function is defined by this equation. We have f of x is equal to g of x over h of x, where h of x is not equal to 0. So basically what this is saying is f of x is just a fraction of the polynomial functions. Okay, so we have here g of x, which is a polynomial function, and h of x, which is also a polynomial function. So for us to better remember the rational function, the numerator is a polynomial function and the denominator is also a polynomial function. And this denominator should not be equal to 0. Okay, next. So example for the rational function. So f of x is equal to x over x minus 1. We know that x here is a polynomial function and x minus 1 here is a polynomial function. Hence, f of x is a polynomial function. Is a rational function. Next, g of x is equal to 1 over x squared minus 1. So this one here is also a polynomial function because we have learned a while ago that the constant function is a special type of a polynomial function. So the numerator is a polynomial function and the denominator is a type of function which is a quadratic function, which is a polynomial function as well. Okay, so the graph here is, well, we have to learn that rational function has asymptotes, what we call asymptotes. So asymptotes, what are these? Basically, these are the lines such that the graph should not touch this. Okay. Oh, so the definition is kind of vague, but this is where the line or the graph goes closer and closer, but it doesn't touch. Okay. So for example, we have here the vertical asymptote, the horizontal, and the oblique or slant. Okay. So let's give an example for this. So this one. So for example, we have here the asymptotes and asymptotes here, there. We have the vertical asymptote and the horizontal asymptote. Okay, so the graph would look like this. Let's use another color. So, oops, I don't like the graphing of that. Okay. Okay, there. So, and then this one here. So this is an example of a rational function. So as you can see, the part here, the graph that we have, the orange one, the orange arrow, it goes upward. Okay, it goes upward and it goes nearer to the asymptote. But we have to remember that this orange line, while it goes upward, it goes nearer and nearer to the asymptote. It doesn't touch the asymptote, no matter how big or how large our number is. Okay? No matter how high the y value of this orange line. And the same for other parts here. This one, and this one. So, for rational function, again, we have to remember that there are asymptotes. Okay? Next, radical function. So radical function is defined by this equation. F of x is equal to nth root of g of x, such that the one inside, which is the g of x, is a polynomial function. Okay? And the one outside the radical sign, which is the n, it should be a non-negative integer, meaning it should only be, it shouldn't be negative, basically. And it should be greater than 1. So, for example, 2, 3, 4, ellipses. It cannot be any fraction. Okay? So, if you see any radical sign, such that that radical sign contains any variable, then it is considered as a radical function. So, for example, of f of x is equal to square root of x. As simple as this one, this is considered as a radical function. So, another example for the radical function is cube root of 1 minus x. Okay, so again, the one inside here, oops, there. The one inside the radical sign, it should be a polynomial function. Okay, next, h of x is equal to square root of, let's say, 3x minus 1 plus 1 is still considered as a radical function. Okay, next, exponential function. So for the exponential function, it is defined by the equation f of x is equal to a raised to x. So the a here is a number. Okay, it could be any number, but it has restrictions. The restrictions are, it should be positive, okay, and should not be equal to 1. Okay, we have the note here, 0 raised to 0 is the indeterminate. So let's give an example for the exponential function. So f of x is equal to 2 raised to x. This is an example of a polynomial function, of an exponential function. The 2 here is called the base. Okay, and the x here is called the exponent. Okay, another example, g of x is equal to 3 raised to x plus 1. Okay, so again, we have the base 3, and we have the exponent x plus 1. Another example, h of x is equal to 4 plus 5 raised to 1 minus 2x. Okay, so again, here we have the exponent such that it has exponent, I mean a variable. So how about this one? Let's use this one and then clear. Okay, how about f of x is equal to x squared minus 2x plus 1. Is this an example of an exponential function? Okay, for this one, obviously it's not. Okay, it's not an example of an exponential function because although we have exponents here, the exponent is a number and it doesn't have any variable. Okay, the premise of the exponential functions is that the exponent should have a variable. And this one is actually the one that we have discussed earlier, which is called a quadratic function. Quadratic. There. Okay? Because it has degree 2. Okay? Let's proceed with another one. Logarithmic function. So logarithmic function is defined by the equation f of x is equal to logarithm of x to the base a, such that a is again a positive number and a should not be equal to 1. So for this one, the part here, it should always have a variable, okay? And then again, we have another base here, and this base could be any number. So for example, f of x is logarithm of x to the base 2. Okay. Next, f of x is logarithm of x plus 1. So if we don't see any number here or any base here, okay, by default, the base here is 10, okay? So this is equal to logarithm of x plus 1 to the base 10, okay? Again, if you don't see any number here, any number in the base, by default it's 10, okay? So for another example, or counter example maybe. So counter example for this is, let's say we have x plus logarithm of 3 to the base 2. So this one here is not a logarithmic function. Why? Because although we can see the logarithm here, the part here doesn't have any variable, okay? So basically it's just a number. It's just a constant, okay? So for this one to be a logarithmic function, the part here where the 3 is positioned into should have any variable. So for example, as simple as 3x or logarithm of 3x to the base 2. Okay? Now, according to this according to the definition, the inverse of the logarithmic function is an exponential function. So, and vice versa, the inverse of the exponential function is the logarithmic function. Okay? Next one, piecewise defined function. So for piecewise defined function, according to the definition, it has more than one formula or equation. And these formulas are constrained into different pieces of the domain, meaning it has different intervals. It has different boundaries based on what this is actually crosses. So the input it describes situations in which a rule or relationship changes as the input value crosses certain boundaries. So if we see any function that looks like this, so f of x is equal to braces, let's say braces, and we see that it doesn't just have one formula because it has a lot of domains, then it is called a piecewise defined function. Okay, so example for this, simple as f of x is equal to x if x is greater than 1, and 1 minus x if x is less than or equal to 1. Okay, so for this particular example, we have two domains. The first domain is x such that it should be greater than 1. For example, 2 or 1.5 or 1.05 or 100, okay? And if x is 100 or it's greater than 1, we are going to use this equation, okay? But if our domain or if the value of x is less than or equal to 1, for example, 0, -1, -100, negative 1.01, we're going to use the one below, okay? This one. So another example of a piecewise defined function is f of x is equal to x squared and negative x plus 1, such that x here is less than -2 and x here is greater than or equal to -2. Okay, so for example, if we evaluate this one, if for example I would like to get the f of x if x is equal to let's say -3. So x is equal to -3. It falls under which domain? So it falls under this domain. Okay, x is less than or equal to -2. And since it falls under this domain, what we're going to use is the one above. Okay, so f of x is equal to x squared, which is equal to -3 raised to 2. And finally, we have 9. But if x is equal to 0, we're going to use the one below because it falls under this domain. So x is greater than or equal to -2. So what we have here is f of x is equal to -x plus 1, which is equal to 0 plus 1. And finally, we have 1. Okay? So that's what a piecewise defined function is. And then another information is that an absolute value is an example of a piecewise defined function. Okay? So let's see. So for example, we have f of x is equal to absolute value of x. And we know that for any value of x, f of x is always positive. Okay? So we can actually separate the values of x. We have here the x and the negative x. Okay? So we can transform this absolute value function into a piecewise defined function. So f of x is equal to braces x and negative x. If this is x, then our domain is greater than or equal to 0. And negative x if x is less than 0. Okay, let's see. Let's try to evaluate it if this actually coincides with the absolute value function. So for example, I have here x is equal to 1. So this falls under this domain. Our x or f of x is equal to 1. But if, for example, I have x is equal to -2, it falls under this domain. X is equal to less than 0. So we will use this equation, the one below. So f of x is equal to negative of -2, which is positive 2. So we see here that the output or the f of x always brings out a positive number. So here we have transformed the absolute value function into a piecewise defined function. Okay, so what's the graph of this absolute value function or the piecewise defined function for the absolute value? So let's see. So we have here the Cartesian plane. And since it's always positive, no matter what the domain is, what the value of x is. So we have here this one here. This corresponds to the domain x is greater than 0, greater than or equal to 0. And this one here this corresponds to the domain x is less than 0, the one here. Okay, so this is the absolute value function. Okay, so here are the types of functions. We have the graphs of these functions. So for example, linear function, again, this is a line. If this is negative, it should look like this, negative slope. And we have the quadratic function, which is called the parabola. Okay, the coefficient of x squared here is positive, and if it's negative, then it should look like this. And then we have the constant. So the graph of the constant is a horizontal line. We have here the rational function, where we don't see any asymptotes here because asymptotes are again imaginary lines. So we can like assume that the asymptotes are here, and it never touches the graphs here. Okay. Next, we have the radical function. Okay. We have the exponential function, the logarithmic function. Again, the logarithmic function is the inverse of the exponential function. And the inverse of the exponential function is, of course, the logarithmic function. And we have here the piecewise defined function. So the piecewise defined function, again, it has two or more graphs or curves. Okay, so if we have three equations or three formula, we can observe three types of or three counts of graphs or curve in the Cartesian plane. Okay, so that's it for the types of function. But before we end, let's try to answer some questions. So for this one, we have to identify if the given equation is we have to identify the type of function given the equation. So for this one, for the first one, so we can observe that it has exponents. And the exponent here has variable. So this one, the type of function of this function is called the exponential. Okay. Next, second, we can observe the logarithm sign. Okay. And the one here, again, has variables. So this is called the logarithmic function. Okay. And lastly, so we can see that the function has more than one formula. It's 1 if x is rational and -1 if x is irrational. Okay, so this one here is called the piecewise defined. Okay, next, so we have to identify again the type of function using the given curve. Okay, so for this one, for number 1, obviously this is called a linear function because it forms a line in the graph or in the Cartesian plane. Okay, linear. Second, we have encountered this already. So it has two types of or two graphs in one Cartesian plane, the one here and the one here. So this is called the piecewise. Okay. And lastly, the one here is a parabola. So this one is a quadratic. So now we're done with the types of functions.